Welcome to this class. Okay, so we're going to be dealing with exercises from exercises for the course heat energy, which we just concluded, and we have 4 questions for this video, and we're going to be doing that briefly. Okay, if you want the questions, you could of course get it downloaded from you can get the PDF version downloaded from the description of these videos. Okay, so let's dive right in. Okay, so the first question we have here says a round hole of diameter 4 centimeters at 0 degrees Celsius is cut into sheets of brass. Our coefficient of linear expansivity is given. The question is find the new diameter of the hole at 40 degrees Celsius. We have our parameters. We have D1, we have T1, we have T2, we have alpha, which is our linear expansivity. We're asked to find D2. Okay, I would want to solve this with the superficial expansivity formula. That's the area expansion formula. Okay, so the beta is equal to change in area over unit area per degree rise in temperature. Okay, so that we equate that to 2 alpha. So we're going to use 2 alpha in replacement for beta, which is the superficial expansivity. So if we move on, put in our parameters, 2 times linear expansivity will give us change in area, which is pi d minus pi d all over pi d times 40 minus 0. I'm sure you know that the area of, it's a hole, so it's a circle. The area of a circle is pi r squared, or pi d. Okay, so we factor out pi from that equation. We'll bring out pi. That's, we'll have pi brackets, okay, d2 minus d1. All right, so if we have this, and of course if we factor out pi like this from this numerator here, okay, we can see that we have pi out, and this pi can divide this pi down here. So that would leave us with d2 minus 4cm all over 4cm times 40 minus 0, because of course our pi's are gone. If we find a way to make d2 the subject of formula, as we can take all this to this side, multiply it with this, and then add 4 centimeter to this other side because of negative sign. All right, I'm sure we can handle that. This will give us d2. So further simplification will give us our answer as 4.00608 centimeters. Okay, so let's move on to question number 2. A cup made of Pyrex glass has a volume of 200 centimeter cube at 0 degrees Celsius. If the coefficient of linear expansion is 0.00003 per Kelvin, what will be its volume if it holds hot water at 92 degrees Celsius? Okay, so we have our parameters V1, T1, T2, and alpha. We're asked to find V2. Okay, but in this case, of course, we're given alpha when we're asked to find volume. So we know the relationship between cubic expansivity and linear expansivity. So we use that to our advantage. So we replace cubic expansivity here by 3 alpha. And if we do that, we're going to have V2 minus 200 all over 200 times 92 minus 0. Okay, so basically, we're not converting, of course, our alpha is in per Kelvin, but we're not converting the unit of our temperature to Kelvin. And that's because we're dealing with difference. So as long as you're dealing with difference, it doesn't matter what scale you're on. If you subtract both temperatures in Kelvin scale, it will give you exactly the same answer it will give you if you subtract both temperatures in the degree Celsius scale. So if we simplify this, we obviously get V2 minus 200 divided by 18400 centimeter cube. Okay, so here we make V2 the subject of formula. Okay, we have 3 times 0.00003 per Kelvin, all right, times 18,400 plus 200 centimeter cube, all right, to be our V2. If we solve that, simplify that with a calculator, we would have 201.656 centimeter cube. All right, so let's move to number 3. A solid metal cube of side 10 cm is heated from 10 degrees Celsius to 60 degrees Celsius. If the linear expansivity of the metal is 1.2 times 10 raised to the power minus 5 per Kelvin, calculate the increase in its volume. So the parameters we are given is L1 10 cm, T1 10 degrees Celsius, T2 60 degrees Celsius. alpha 1.2 times 10 raised to the minus 5 per Kelvin. We have to find the change in volume, not V2. Increase in its volume is the change we're looking for. If you look at this question very well, it's quite tricky. So the metal cube of side 10 centimeter, we have one side, okay, but we're asked to find the volume, and we know volume is length times length times length. So we have L cube for volume. So whatever side we have, we find the cube of it. All right, so we use the formula that equates volume expansivity to, or volume expansion to linear expansion, and we're doing that because we're not given the volume expansivity of the metal, we're given the linear expansivity of the metal. So we need to use alpha to equate with this we have on this side and solve for our change in V. All right, so we have V2 minus 10 raised to the power 3, 10 from the side of the cube, that is 10 centimeter. So we're finding the cube of that, so we can get the volume L3. So 10 cube, V2 minus 10 cube centimeter cube divided by V1, which is 10 cube, all right, times change in temperature, which is 60 minus 10. Okay, all right, so if we simplify this, we're going to be having 50,000 centimeter cube. Okay, making V to the substitute of formula, we have 3 times this is 50,000 plus 1,000. I'm showing how to get the substitute of formula. If you don't, you can look out for a mass course that handles that and look through it when it's up and running. Okay, so this will equate to 1001.8 centimeter cube as our V2. All right, so we go ahead to find our change in volume, which is 1001.8 minus 1000 centimeter cube, which would give us 1.8 centimeter cube, and that's our answer. All right, an iron rod is 1.58 meters long at 0 degrees Celsius. What must be the length of a brass rod at 0 degrees Celsius if the difference between the lengths of the two rods is to remain the same at all temperatures? So the linear expansivity of iron is given, linear expansivity of brass is given. Okay, so basically the key sentence in this question is if the difference between the lengths of the two rods is to remain the same at all temperatures. All right, so the difference between the iron rod and the brass rod at 0 degrees Celsius, that difference remains the same even at 1 degree Celsius, even at 200 degrees Celsius, even at 300 degrees Celsius. Okay, so which means that at any other temperature apart from, if you're considering any other temperature apart from 0 degrees Celsius for both iron rod and brass rod, the L that's change in length for iron rod automatically will be the same for the brass rod. Take a moment and think about it. Okay, so let's say for iron, okay, L1 for iron is 1.58. all right, and then here we have for brass. Okay, so let's assume L1 for brass is let's take 2.58. Okay, so L1 is 2.58 for brass, and this is at T1 for both of them. Here is 0 degrees, okay, Celsius. Okay, and T2 we have let's say 10 degrees Celsius. So at T2, let's say L1 is 2.58 at 10 degrees, right? Now what will L1 of brass now be? Because the statement says the difference between the lengths of the two rods is to remain the same at all temperatures. That means the difference between 2.58 and 1.58 will be the same difference that this iron and brass will have. So it means 2.58 minus 1.58 is 1. So it means that at this second temperature T2, that difference will be maintained. So L1 for brass automatically will be 3.58. Okay, and the difference is maintained. Okay, so what is the difference between both of them? 1. The difference is 1. All right, that's 1 meters. Okay, so this is L2 and this is L2. Okay, so if the difference in length between the iron and brass at L1 is 1 meter, it means the difference in length between iron and brass at T2 is going to be 1. So if L2 is 2.58 for iron, L2 for brass should be 2.58 plus 1 to give us 3.58. Now, the same way, the L now for L1 and L2 should be the same DL for L1 and L2 brass. Think about it. So we have change in length for iron, that's L2 minus L1, to be 1, and change in length for brass, L2 minus L1, to be 1. So you see why I said that sentence carries the understanding that will aid your ability to solve this question. Okay, so let's move on to solving the question. So now we're concerned about change in length because we've realized that the change in length, the L for iron, okay, is always going to be the same at any given temperature with the change in length for brass at that particular temperature. Okay, so the L for both metals are the same. That's the idea that sentence brings to the table. For iron, our change in length, okay, because we can find change in length for iron because we have the parameters that we need. So we have alpha, we have L1, and what we don't have is change in temperature. Okay, so we're going to be solving this question in 2 ways. I'm going to do one other way that is quite abstract. Okay, then I'm going to do a second one that is more straightforward and mathematical, nothing abstract in it. Okay, so we have alpha, we have L1, we don't have change in temperature. Okay, but now the idea is we've been told at any temperature at all, this rule stands. So we can assume any temperature to solve this problem. Okay, so I'm going to be assuming our T2 to be 10. Our T1 is 0 degrees Celsius. So I'm going to assume our T2 to be 10 degrees Celsius. So change in temperature will be 10 minus 0, which will be 10. Okay, so we assume the change in temperature to be 10. So we bring in our variables, 1.2 times 10 raised by minus 5 for iron, then L1 1.58 times our assumed change in temperature. All right, so if we multiply that out, we have 1.894 times 10 raised by minus 4. Okay, so it means if this is the change in length iron goes through, okay, when its temperature is increased from 0 degrees Celsius to 10 degrees Celsius, then we're going to have that same change in length when brass is increased from 0 degrees Celsius to 10 degrees Celsius. Remember, we're not talking of L1 and L2. The values of L1 and L2 will be different for both metals, but the difference between that value L1 and L2 is maintained. That's the idea, don't forget. Okay, so for brass now, we can't really find the L for brass because we don't even have L1. We can't even find the L for brass, okay, at an L2 of 10 because we don't even have L1. Okay, so for brass, since we already have change in length, okay, for brass, we can go straight into finding L1 for brass, all right, which is what we were asked to find. So we have the L already. The L happens to be the value we got for iron. We have alpha already, which is given here. Our change in theta, we have that already as 10, okay, because we're comparing, we're working with a T1 of 0 and an assumed T2 of 10, okay, because we're told that the difference remains the same. The difference between the length of the rod remains the same at all temperatures. So no matter the change in temperature, no matter what value it is, okay, your DL for iron at that same change in temperature is your DL for brass. So we put in our parameters. Change in length 1.894 times 10 raised by minus 4 from what we got here. Then we have alpha, which is the linear expansivity of brass. Then we multiply it by 10, which is the change in temperature which we presumed or assumed. Okay, so we'll get our final answer to be 0.997 meters. Okay, but now let's try to solve in another way. Now, one other way to think about it is, since change in length is the same for both metals, we can equate their change in length. Okay, so we have alpha I, which is for ion, L1I, which is for ion, change in temperature I, which is for ion, is equal to alpha B, which is brass, L1B, which is brass, and change in temperature B, which is brass. And all this equates to the change in length, okay? Because we know change in length is L1 alpha change in theta, okay? If we make L1 the subject of formula here, this is what we have, okay? So we are equating that change in length for both metals. And if we do so, we cannot make L1 the subject of formula, okay? If we make L1B the subject of formula, this is what we're going to have, okay? So all we need to do is to put in our parameters and we're good to go. But then before that, remember that theta I, which is for ion, and theta B, which is for brass, has to be the same. So, and this is division sign. That automatically means that this guy is going to take out this guy here, okay? All right, so we'll be left with LIB equal to alpha I L1I, okay, divided by alpha B. All right, so putting in our parameters, we have 1.2 times 10 raised to minus 5, that's alpha 1, times 1.58, which is L1I, that's L1 for ion, all right, divided by alpha B, which is 1.9 times 10 raised to minus 5, okay? We didn't need to make any assumption for temperature here, but then we could still get that our answer is 0.997 meters.